Okay, we're going to use the method of integration by substitution to do definite integrals. Here you got to be really careful because when you make a substitution, your limits of integration are going to change. Like for example, here, these are x limits. That's x equals 0, x equals pi over 2. If I do a u sub, I'm going to have to change my limits. Now, I'll show you a shortcut you can use where you don't have to change your limits by doing an indefinite integral as side work, but you got to be really careful writing that up. And I see students write up, they might get the right answer, but they write it up incorrectly. You will never, ever, ever, never have a definite integral, some f of x dx, equal an indefinite integral. What I've written here makes no sense whatsoever. An indefinite integral with no limits on it, this is a function. Your answer is a new formula, a new function. A definite integral, your answer is just a number. It's the area under a curve. You will never have a definite integral equaling an indefinite integral. That doesn't make any sense. So I'll show you a shortcut, but we got to be careful how we write that up. We're going to do a bunch of side work and not put an equal between things that are not equal. Okay, let's take a look at this problem. I want to do this definite integral, sine squared cosine dx from 0 to pi over 2. So let's do a u sub. So think about it for a second here. What's the derivative of sine? Derivative of sine is cosine. So if I let u equal sine of x, then this will be u squared. And I've got du sitting right here in front of me. Du will be cosine of x dx. So I could rewrite this equals the antiderivative of u squared du, but that equal sign that I just wrote is a lie. That's a definite integral. That's a number. That's an indefinite integral. That's a function. There's no way those are equal. I'm not done. I have to change my limits. When x equals 0, u will be sine of 0, which is still 0. But when x equals pi over 2, that implies u is sine of pi over 2, which is 1. So these were x equals limits. Now that I've switched to u, I need my u limits. So when x equaled 0, u was still 0. But when x was pi over 2, u will be 1. When you're doing integration by substitution, you got to change your limits. By literally just plugging in. I'm plugging in these x values into here and finding out what those u values will be. Okay, and then this is an easy problem. That will be u cubed over 3 evaluated from 0 to 1, which will be 1/3 minus 0, which is 1/3. We're done. Now, here's a shortcut you can use. I don't know how much of a shortcut it is, but it's like an alternate approach. So here's our original problem. I'm going to do the whole thing from the beginning. I'm going to do side work to find an antiderivative of this integrand. I'm not going to put an equal sign here. This is the most, it's trivial. It seems like a minor thing, but it's important. I am not going to put an equal sign here. I'm going to do side work and do the general antiderivative of sine squared x cosine of x dx. Forget about that definite integral. I'll come back to him. Like it's a lot of the same work here. U is sine of x. Du is cos of x dx. Then that guy's antiderivative will be antiderivative of u squared du. There's du. There's u squared. That'll be u cubed over 3 plus c. Now, let's plug back in our u. So that'll be sine cubed over 3 plus c. Now that I know what the antiderivative of this is, I can go back to the original problem and just do him in terms of sine, or in terms of x from the beginning. This definite integral then, I know this guy's antiderivative is sine cubed over 3, evaluated then, because this is a definite integral, from 0 to pi over 2. And now I can just do everything in terms of x. So this will be sine of pi over 2 cubed over 3 minus sine of 0 cubed over 3. Sine of pi over 2 is 1. I get 1/3. Sine of 0 is 0. I get 0. I get 1/3. Okay, so every integration by substitution, definite integral, they're all the same. You just got to be careful on how you write it up. If you're switching over to u's and you want to forget about x's, then you have to change your limits. And then from that moment on, forget about the original x's. It's a brand new problem. You just finish out with u, you get your answer, you're done. Or alternatively, sometimes it is easier to do some side work and find a definite or an indefinite integral. Find the antiderivative of the inside. Then go back and do everything in terms of your original variable and leave your limits alone. But this is all side work. Don't ever put that this equals that, because these are not equal. This is a number. This was a function. I find it typically easier to change the limits. When I first learned this, back when I was in your shoes, I would use this method. I would do the indefinite integral and come back. Now that I've been doing this for 25 years or whatever, I think it's you're going to end up plugging it. Look, I get the same numbers. I still plugged in those values. You're doing the same work no matter what. You might as well just go ahead and change your limits. So all the rest of the examples I do today, I'm going to change the limits. I'm going to use this method. I just want you to be aware there is another way where you don't have to change the limits, but you got to do it as side work. All right, I'll put all the rest of these examples in a different video.